Just looking at finite temperature behavior, so we could ask what happens if you have chemical potentials, so that we can have a more non-trivial phase plot and see what happens. So chemical potentials in n equals 4 super young. So I had mentioned that at some point that the n equals 4 theory has a global symmetry, SO6R. And this means, if you look at the SO6, this contains 3 commuting U1s. So that means there are 3 independent U1 charges for each of which you could imagine introducing chemical potential. So there can have 3 chemical potentials for each of these charges, and the fields of the theory are charged, and all the fields carry, all the matter fields carry charges under these 3. Let me not explain what the charges are, but both the scalars and fermions are charged under these chemical potentials, under these U1s. So when you introduce a chemical potential for this, you find that it will have a non-trivial effect on the phase diagram of the system. So you can now modify this weak coupling calculation to include the effect of these chemical potentials. So let me just tell you what the final result is, because you can sort of see that where it's going. So at weak coupling, there are some interesting things that happen depending upon what pattern of chemical potentials you choose, and it's not really worth spending too much time on that. All you need to see is the gross features, weak coupling on S3 cross S1. So let me just draw the phase diagram. So you find that n equals 4 theory at arbitrary weak coupling on S3 cross S1 and in the large n limit has the following phase diagram. So temperature, chemical potential, where this mu could be any one of those mu's or some combination, it doesn't matter. So the general phase diagram has this there is a line, and then there's another line maybe
which mu are you?
it could be any one of them. I don't want to get into it. It doesn't matter. Actually. Could be any one of them. Could even be some linear combination of them. Could be some charges, linear combination of these charges. It doesn't matter. Some details change, but the gross picture is always the same. Okay, this qualitative picture is always the same. So what's happening in all these different regions is the following. Here you have the n equals theory, 4 theory is realized in a Zn symmetric phase, which means that it's confined. So Zn symmetry unbroken means the theory is confined. And here the Polyakov loop has 0 expectation value. This is a special point, mu equals 1 happens to be a special point where I've set the radius of the S3 to be 1. And mu equals 1 is a special point, and I'll tell you in a minute what it is. This here is Zn broken. This entire phase is Zn broken, deconfined. And there's this thatched region. So the fact that the theory is deconfined and is at finite temperature tells you that it's a plasma phase, right? So this whole region is like a plasma, deconfined plasma phase. And the thatched region happens to be a deconfined but metastable plasma phase. And then in this region something bad happens. The theory doesn't have a stable ground state. So there's a whole region of the phase diagram that's effectively excluded because the theory doesn't have a stable ground state. But what happens here is that in this region, it's kind of interesting. It's already intriguing why this is, what causes this instability. It's actually not that difficult to understand. The instability is due to the fact that you have scalar fields in the theory. Okay, and when you add a chemical potential for charged scalar fields, you know from just basic, say, lambda phi to the fourth theory, that you get Bose-Einstein condensation. Okay, so chemical potential for a charged scalar acts like a negative mass squared. So this instability is because charged scalars, they've got charged scalars implies that in your action, so when you introduce a chemical potential, you need to shift your Lagrangian by something that looks like mu times the current density or the charge density, right? That's one term. But when you have scalars, you get an extra piece. You get an extra piece that looks like phi dagger phi, minus mu square phi dagger phi. Okay, and perhaps one should keep in mind that I'm working in Euclidean, so that a positive mass squared actually in the Lagrangian means plus m squared. Negative mass squared means minus mu squared. So this acts like a negative mass squared term. So effective negative mass squared. Now, what happens usually in lambda phi to the fourth theory is that this negative mass squared term is countered by the lambda phi to the fourth interaction. So you get Bose condensation. The point about n equals 4 theory is that there is a phi to the fourth interaction in n equals 4 theory. N equals 4 also contains a term in Lagrangian which looks like trace let me just write it schematically. Looks like trace phi dagger commutator square. Its effective potential contains this. So this is not a usual phi to the fourth term because it involves the commutator of fields. So there are directions where this phi to the fourth, actually this phi to the fourth interaction is actually exactly 0. It's 0 whenever phi commutes with phi dagger. So you can choose to be in a diagonal basis, and when the phi's are diagonal, so that's what we call the Coulomb branch of the theory, where if phi's are diagonal, the gauge group is broken to some SUN is broken to U1 to the n minus 1, and these are flat directions. So when you don't have chemical potential, these are flat directions. This is just the so-called moduli space of n equals 4 theory. When you introduce this chemical potential, it destabilizes that moduli space. What it means is that in the grand canonical ensemble, because it costs no energy, because there are these flat directions in the original potential energy, it says that when you introduce a chemical potential in the grand canonical ensemble, it costs, there's no free energy cost to producing configurations with arbitrarily large amounts of that U1 charge, because there was no potential energy in that direction in the first place. So this kind of instability is always going to be there in any theory which has flat directions to begin with. And then you introduce a chemical potential along some charged scalar direction, you will find that it has an instability. But this is interesting because it's an instability towards condensation of scalars. It doesn't have an endpoint, but it's interesting because it's like instability towards Higgsing. Unfortunately, it doesn't have an endpoint. If it had an endpoint, it would be a state with Bose-Einstein condensate where the gauge group was Higgs, and there would be a stable ground state. So, sorry?
Now it's just theory is unstable and wrong.
Now this is just runaway. Yeah, it's just runaway. But it's runaway in a way where all these condensates are non-zero in the direction where these condensates. So if you stare at this, I'll come back to this maybe when I start with the transparencies. You can start seeing some weird similarities to the QCD phase diagram.
But how come there is an onset of the mu?
Why is it mu equals 1?
Right.
Good, very good question, because actually there is an extra term here which I mentioned, which was the mass of the scalars due to the conformal coupling to their curvature. So there actually the n equals 4 theory on S3 cross S1 contains that, but it also contains a term which is just trace phi dagger phi times 1, where 1 over r, where that 1 is 1 over r squared. So there is an onset value indeed. Good question. So that 1 is there simply because you're studying the theory on S3. Okay, and so and then but then nevertheless there is actually a region in this in this diagram where, in spite of the fact that the true vacuum of the theory doesn't exist, it's an unstable, there is actually a false vacuum that the theory has, where, and I can explain later why this is the case if you want. But this is the general picture. What is striking, of course, and I want to sort of more or less close this discussion with this story here, is that if you ask what is the phase diagram at strong coupling, lambda goes to infinity. I should say that all of this work is a combination of papers written by Yamada and Yaffe, Yamada himself, and then some work done by us. Then at strong coupling, what you find is that, and this is all around, I think 2000, maybe 2007 or so, 2006, 7. At strong coupling, you can actually do the analysis again, and then you have more non-trivial geometries that contribute. Here you have just thermal ADS. And then here you have a black hole geometry, which is the Reissner-Nordstrom charge, Reissner-Nordstrom ADS black hole. So that's just some charged analog of the ADS-Schwarzschild or big black hole solution. And then Yamada did a careful analysis and then discovered that if you look at these Reissner-Nordstrom black holes, they actually have an instability. It's an instability that's not visible if you look at any perturbative fluctuations in gravity about those solutions, but it's a kind of non-perturbative instability which requires you to introduce D branes. So if you introduce a D3 brane probe, so D3 brane probe feels runaway instability or runaway potential when you introduce it into these geometries. And this runaway potential for D3 brane probes is, according to the ADS CFT correspondence, exactly the same as the instability that you see in the field theory, which corresponds to certain, if you are in the diagonal basis for phi, or the scalar fields phi, the unstable directions correspond to the eigenvalues of this phi matrix becoming arbitrarily large, any one of these eigenvalues. And these eigenvalues are indeed related, are in one-to-one correspondence with positions of probe D branes in this ADS5 cross S5 geometry. So there is one-to-one correspondence between everything that you see at weak coupling and what you see at strong coupling. The details of the shapes of these curves, of course, are going to be different because this is lambda equals infinity. But the basic story looks quite similar. This is unstable. This is metastable. So there's good reason to believe that there is some kind of smooth interpolation going on between weak and strong coupling. It also means that perhaps we should take a little bit more seriously results that may come out of looking at weakly coupled gauge theories in the large n limit, maybe in finite volume. Okay, so the next 45 minutes I'm just going to talk about introducing. Are there any questions about this?
Yes, you talk about looking at the zero masses model, which is corresponding to the upper group.
Yes.
Right now, effective potential, but you start at the UU dagger.
Yeah, that's because it was the Gaussian, it's a free theory, so it doesn't have anything more.
Oh, really?
Yeah, if you take a, I mean,
It's an effective field theory, but
no, it's okay. It's the language of effective field theory, but it's exact. Whatever you're doing is exact at this stage because you're at lambda equals 0. But then if you have non-zero lambda, non-zero 't Hooft coupling, then you will see that you have further higher, higher loop corrections in the 't Hooft coupling, and then you will see that there are complicated polynomial corrections, and those complicated polynomial corrections will change the shape of the potential for the Polyakov loop. And in fact, it's those polynomial corrections that will be responsible for separating the Hagedorn transition from the deconfinement transition. They will separate it. So at lambda equals 0, they're the same, and then later they will be separated. Okay, so we talked about n equals 4 at finite temperature, and then we introduced chemical potential, and there is a kind of more non-trivial phase diagram which matches, or which at least seems to be in strong agreement between weak and strong coupling. So the next interesting question is, what about flavor fields? What if you want to introduce matter fields in the fundamental representation?
Right? So
Yeah.
before you go on, suppose there is a mass correspondence between the weak and strong limits. Then what does this imply? Some duality?
No, I don't think so. It just means that it just means that as a function of the 't Hooft coupling, there is no non-analyticity. Okay, and it also means that probably we can, if we want to think about what properties in the phase diagram of a strongly interacting large N theory we want to look for, at least that's my viewpoint, that you must first begin by perhaps looking at the weakly coupled theory in the large N limit and understanding its thermodynamics, and then using that as a guideline to ask what might happen at strong coupling. But it doesn't mean more than that, anything more than that. It's just an interesting fact that we are able to sort of understand some aspects of the physics on both sides, and we are able to get some kind of dictionary, a handle on what's happening. So in other words, we are not, you don't take ADS-CFT, you don't take an ADS-CFT result that you get from gravity just blindly without understanding what's going on, but at least you can understand its mechanics by mapping it to weak coupling. Something. Okay, so the next thing I want to discuss is, unfortunately this will all have to be very brief, fundamental matter. So how do you introduce matter fields in the fundamental representation, that is quarks? So instead of trying to be very ambitious and trying to have a theory like QCD, which is asymptotically free and well defined in the UV, we might actually consider the most natural way of introducing matter fields in the fundamental representation directly into n equals 4 theory. So n equals 4 supersymmetric Yang-Mills plus matter fields and this subject has been studied to an enormous degree of detail and was initiated by several papers, among which I quote the paper by Karch and Katz. And the basic idea here is that you can, since you are in the large n equals 4 theory, you can continue to imagine being in the 't Hooft large N limit and just introduce quark matter in the 't Hooft large N limit, which means the number of quarks So introduce NF quarks where NF is fixed and NC, or the number of colors, is going to infinity. So that means that in this limit, you only study the quarks in some kind of quenched approximation, that you neglect the loops and therefore the theory. So the way Karch and Katz did this was basically by, will not explain the details, but basically by introducing probe D7 rings. There is a kind of picture of this, cartoonish picture of this, that if you think of all the D3 brains sitting at some point on this board, so the world volume of D3 brains is x0, x1, x2, x3. So all those dimensions are suppressed and they are kind of perpendicular to the board. Then we can imagine introducing D7 brains which span x0, x1 up to x7. So they also span our four-dimensional space-time in which the n equals 4 theory lives, plus extra dimensions. So you can, and we are talking about string theory, so we can always do this. Okay? So when we separate these brains in some transverse dimension, then the strings that stretch between these two, with some orientation, they play the role of quarks. So these guys play the role of quarks. The reason they play the role of quarks is that, well, basically the D7 brains that you introduce have some gauge symmetry that lives on them. But because the D7 brains are higher dimensional objects, the gauge theory that lives on them or the gauge coupling of the gauge theory that lives on them is irrelevant. Which means if you look at low energy limit, the gauge fluctuations freeze out, and what you call a gauge symmetry here becomes a global symmetry. And so this global symmetry is a global symmetry of this combined theory of n D3 brains and D7 brains. So what it looks like is you've got these strings stretching between the D7s and the D3s. This particular endpoint of the string looks like a quark transforming in a fundamental representation of the SUN gauge group that lives on the D3 brains. So that is the cartoon picture. And the mass of the quarks is related to this transverse separation of the D7 brains. And the one other thing that should be mentioned is because all this entire setup preserves a certain amount of supersymmetry, so these are actually n equals 2 quark hypermultiplex. So the entire system preserves n equals 2 supersymmetry in 4 dimensions. Okay, so rather than getting into the details of how to do this, let me just give you a cartoonish depiction of what happens at finite temperature, for example. So there is a non-trivial finite temperature thermodynamics of this system. So when n is large, so when n goes to infinity, you should really be thinking of these probe D7 brains as D7 brains that wrap S3 and are extended in all other directions. If you introduce a finite temperature into the system, which means that you've got some kind of a black hole in AdS5 cross S5, so this is AdS5 cross AdS5 black hole, which describes n equals 4 at high temperature and at strong Hooft coupling. Then these probe brains, which are these quenched quarks, represent these quenched quarks. Well, when you introduce a black hole, this depiction is reasonably accurate. that these branes want to bend towards the black hole simply because of the gravitational attraction. If you make the temperature large enough, there will be a phase transition where these branes actually fall into the black hole. Okay? So there is a phase transition that occurs in this system. So that's T less than some T critical, and for T greater than T critical, there is some new kind of D7 brane embedding that actually falls into the ADS5 black hole. And in this case, T greater than T critical, this kind of transition between these two types of shapes of the D7 branes, one that continues to stay outside the black hole horizon and one that falls into the black hole horizon, you can check by actually computing the spectrum of fluctuations of excitations that live on the D7 brane, that these things can, the transition can be viewed as what's known as a meson melting phase transition. Again, there were more than, I think there was more than one group that was involved in studying this, so perhaps I can give the references later. So there is a non-trivial phase structure that one can introduce or one can see, which is not really deconfinement, but it's deconfinement of quarks, melting of quarks. Okay, so this happens. This happens already in the deconfined, in the phase where the gluons are deconfined, because when n equals 4 theory is described by the ADS5 black hole, the n equals 4 theory is in its deconfined phase. So that means the gluon sector is deconfined, but even when the gluon sector is deconfined, there exists a range of temperatures for which the quarks are still bound. They are bound into mesons. And the fact that they're bound into mesons is encoded in these D7 brane embeddings which don't fall into the black hole. Once they fall into the black hole, these mesons melt, and this is a meson melting transition.
How do you go from the quark picture to the black picture?
From the, say that again, from the
picture with the quark to the bottom.
You mean how to go from weak coupling to strong, or?
No, this picture with the quarks.
Yeah, so these, right, I mean, so in going from this picture is a picture where you haven't taken the n goes to infinity limit. So these are just D3 branes, okay? When you take n goes to infinity, you're going to replace the D3 branes by the geometry that they create, which is anti de Sitter space. So then you don't have this picture anymore. Then the D3 branes have to be removed, and you're just talking about D7 branes in the vicinity of the ADS5 geometry, or inside the ADS5 geometry. So in going from this to this, we have just taken the large and strong coupling limit. So then you don't talk, then actually you're not allowed to talk about individual quarks, because you can't take a string. I mean, if you look at the fluctuations of the D7 brane, then you really should be looking at open strings that end on this D7, both ends of which end on this D7 brane. And then you can look at fluctuations of those, and those are mesons. Those are the meson states. And then when this embedding falls into, when the D7 brane embedding falls into the black hole, that's interpreted as meson melting.
This one is not deconfinement.
It's not deconfinement or glue degrees of freedom, no. That's why I said it's meson melting or quark liberation. So, and this picture with some modifications continues to hold also when you introduce a baryon number chemical potential. So you can again get some kind of phase plot, temperature versus baryon number, because now you have quarks, so you can, there is a U1 baryon in the system, so you can introduce a baryon number chemical potential. And there is a similar story. I will not explain too much detail what happens. It's quite an intricate story. So what happens is that so this is n equals 4 plus